we've dealt so far with the case of certainty, and we've done almost as much as we could in certainty. And I now want to move to the case of uncertainty, which is really where things get much more interesting and things can go wrong. So I'm going to cover this. OK, so we're ready to start. So far all we've considered is the case of certainty. So with uncertainty, things get much more interesting. And I want to remind you of a few of the basics of mathematical statistics that I'm sure you know. So you know we deal with random variables which have uncertain outcomes, but with well-defined probabilities. Okay, so another step that we're not going to take in this course is to say people just have no idea what the chances are something's going to happen. Schiller thinks we live in a world like that, where, you know, who knows what the future's going to be like, and people, they hear a story and then everybody gets wildly optimistic, and then they hear some terrible story and then everyone gets wildly pessimistic. You know, and that kind of mood swing can affect the whole economy. I'm not going to deal with that. It's hard to quantify, and I'm not exactly sure it's as important as he thinks it is. So we're going to deal with the case where many things can happen, but you know what the chances are that they could happen. And still, lots of things can go wrong in that case. So there are a couple things that words that I want you to know, which we went over last time, but I'll just do an example. So suppose we always deal with states of the world. Okay, states of nature, that was Leibniz's idea. So let's take the simplest case where with probability of half you could get 1, and with probability of half you could get -1. Okay, so that's a random variable. It might be how your investment does. Half the time you're going to make $1, half the time you're going to lose $1. So we define so this is x. So we define the expectation of x, which I write as x bar, as the probability of the upstate happening. So let's just call that 1/2 times 1 plus 1/2 times -1, which equals 0. Then I define the variance of x to be what's the expectation of the square difference from the expectation. So how uncertain it is, you're sort of on average expecting to get 0. So uncertain it is measured by how far from 0 you are, but we're going to square it. So it's 1/2 times 1 minus x bar squared plus 1/2 times -1 minus x bar squared equals 1/2 times 1 plus 1/2 times 1, which also equals 1. So the variance is 1. And then I'll write the standard deviation of x equals the square root of the variance of x, which equals the square root of 1, which is also 1. So very often we're going to use the expectation of x. That's going to be how good the thing is. And the standard deviation is going to be how uncertain it is. And people aren't going to like, soon we're going to introduce the idea that people don't like uncertainty. And this is the measure of what they do like. It pays off on average a big number, say. This one doesn't, but it could. And the measure of uncertainty is the standard deviation. I choose that rather than the variance for a reason you'll see. It makes all the graphs prettier. But also, if you double x, you'll double the expectation, obviously, because you just double everything inside here. The variance, though, you're going to end up squaring the two. If you double x, you'll double all these outcomes and the mean, so you'll end up multiplying the variance by 4, whereas you'll multiply the standard deviation by 2. So rescaling just rescales these two numbers and has a funny effect on that number. So that's the reason why we use these two. OK, now you could take another example, by the way, which is 0.9 times 3. Let's call this y. And 0.1 times minus something. How about, let's call this 1/3 and this minus 3. OK, now what's the expectation of y? The expectation of y equals 0.3. Right, let's just write it out, is 0.9 times a third plus 0.1 times minus 3, which equals 0.3 minus 0.3, which equals 0. So the expectation of this random variable is the same as the expectation of that random variable. And now the variance of this, of y, is 0.9 times a third minus 0 squared plus 0.1 times minus 3 minus 0 squared, which equals 0.9 times 1/9, right, plus 0.1 times 9, okay, which equals 0.1 plus 0.9, which equals 1, which is the same as the other one. So here we've got another random variable, which looks quite different from this. So clearly, standard deviation and expectation don't characterize things. This looks quite different from that one, has the same standard deviation and the same expectation. Okay, so we're going to come back to what the differences between these two variables in a second. So there's another thing I want to introduce, which is the covariance of x and y. Okay, so we could look at the outcomes of these variables. Where am I going to write this? We could look, I'll write it over here. We could look at the outcome of these variables in a picture like this. And so here we have x and here we have y. So x could turn out to be 1 when y is a third. Okay, and x could turn out to be 1 when y is minus 3. So here's an outcome and here's an outcome. And x could be minus 1. And we could get a third or minus 3. So there are 4 outcomes which looked at here. Okay, so if you looked at x alone, it's got a 50-50 chance you're here or here. If you look at y alone, it's a 90% chance up there and a 10% chance down there. So those are called the marginal distributions. But the joint distribution, we would have to add a number. So if you looked at x alone, by the way, you would say x alone, you would say here's 0, here's 1, here's minus 1. So you could have this or this with probability a half and a half. And y, you know, you could have, so we'll do it this way. With y, you could have a third or minus 3. And here the probability is going to be 0.9 and 0.1. So that's what we have. Those are the, this is 0. Those are the pictures that we started with. Okay, so you know where x could end up and where y could end up. Well, you don't know where they jointly could end up. So if they end up on the long diagonal, that means when x is high, y tends to be high, and vice versa. If you end up down here, x is low and y is low. So to the extent that the probability is on the long diagonal, they're correlated together. To the extent that the probability is on the off diagonal, they're negatively correlated. So anyway, to get a sense of that, the covariance is going to be the probability of 1 comma a third times 1 minus x bar times a third minus y bar, okay, plus the probability of, I'll just go around the circle, of minus 1 comma a third times minus 1 minus x bar times times a third minus y bar, okay, plus the probability of minus 1 and a third. Sorry, what did I just do? I did minus 1 and a third. I've already done that. So I'm down here. So minus 1 and minus 3 times minus 1 minus x bar times minus 3 minus x bar plus probability of the ordered pair.
Should that minus 3 be x bar or y bar?
Thank you. And probability, what's the point I haven't done yet? 1 comma minus 3 times 1 minus x bar times minus 3 minus y bar. Okay, so now why does that covariance pick up the idea of correlation? Well, to the extent that the probabilities are high here and over there, on the long diagonal, this term is going to get a lot of weight. And what is the other term? minus 1, minus 3, and this term is going to get a lot of weight. So to the extent that you're on the long diagonal, this term and this term are going to get a lot of weight. But you see those terms, this is going to be positive because it's 1 minus 0 and a third minus 0, so that's a positive term. And this is negative, minus 1 minus 0, minus 3 minus 0. So negative times a negative is also positive. To the extent that you're down here and up there, you're going to get big positive numbers in the covariance. To the extent you're on the off diagonal, you'll get big probabilities here, but they all multiply negative terms. This is a minus and this is a minus because one of the terms is above the mean and the other one's below the mean. That's what it means to be in the off diagonal. So covariance is giving you a sense of whether things are moving together or moving the opposite way. Okay, so those are the basic things that you have to know. And I guess another couple things are the covariance is linear in x, right? Because if you double x, every time you see the x variable, over here it's always an x outcome minus an x bar, an x outcome minus an x bar, an x outcome minus an x bar, an x outcome minus x bar. So if you double x, you're going to double every term. So it's linear in x and in y. And so one last thing to keep in mind is that the variance, so the variance of x is just the covariance of x with itself. Obviously, if you just plug in x equal to y, you just get the formula for covariance. Okay? And similarly, because they're linear, the covariance of x plus y with its, so the variance of x plus y, one more formula, of x plus y by linearity, well, first of all, that's the covariance of x plus y with itself. And therefore, by linearity now, I'm just going to do linear stuff. That's equal to the covariance of x with x, okay, and plus the covariance of y with y, plus 2 times the covariance of x with y. So I could take, since it's linear, I could just, okay, I just do the linear parts, right? Covariance of x plus y with x plus y is covariance of x plus y with x plus covariance of x plus y with y. Then I repeat the linearity thing and I get down to that. Okay, so those are basically the key formulas to know. Okay? So now I'm going to make 3 little observations that come out of all this that are quite fascinating, so quite elementary. Are there any questions about this, these numbers? Yes?
Yeah, I don't understand why you gave the probability of -1, negative 3 weight when negative 3 has a much lower probability of being hit on than 1/3.
Why did we give, say that again?
We underline probability of -1, negative 3.
Probability of -1, negative 3. That's this outcome here. We underlined it not because it was very likely, but because this term is going to be positive. This is positive and this is positive. So the whole point is the joint distribution is not specified, not determined by the distributions of x alone and y alone. Okay, so even if I know the probability of what x could do, and I know what the probabilities that y could do, that doesn't tell me anything about what numbers I should put on these 4 outcomes. For example, I could have at one extreme x, when x is high, y is high. It can't be exactly that because the probabilities are different. So, or I could, you know, these numbers and those numbers don't determine these 4 numbers. Okay, so there are many different numbers I could put in these 4 squares, which would give me, in total, this probability outcome for x, and in total, this probability outcome for y. So an easy way to see that is if I made them, okay? So the distribution now, okay, so what are the observations I want to make? For instance, I could say if x turns out to be a half, then I'll always assume y turns out to be a half. Okay? And then with the other 40% of the time, y might turn out to be, when y is high, x might have to turn out to, so I could have that, you know, so here are some ways I could do this. I could put 50% here, 0.5 here, right? So 50%, then 40% of the time, this is going to turn out, okay, so I have a 0.5 here. Okay, then what could I do with the rest of this? This plus this has to add up to 50%. Okay, and so 50%, I could have x turn out to be here. 50% of the time, x. Okay, so when x is 1, I could have y always turn out to be 1. So that means I must have a probability here of x, of probability 0 here, because here's x 50%. So this plus this, x is going to turn out to be 1 50% of the time. Now, how much of the time is y going to turn out to be down here? 0.1. So suppose I put these probabilities, 0.4. Now, so you see that x is 50% of the time, x is 1, and 50% of the time, x is minus 1. Okay, now how many of the times is y a third? 0.5 plus 0.4, so 90% of the time. And then 10% of the time, y is minus 3. So here's one way of putting probabilities on the dots that produces this outcome. But I could have chosen another way of doing it, the way that you probably had in mind, where I assume they're totally independent. That is, knowing the outcome of x, in this way of doing it, if I know that x turned out to be 1, y has to turn out to be a third. So they're very dependent. X is somehow causing y or determining y. X has a lot of information about y. Suppose I make them independent. I say what happens here has nothing to do with what happens over there. Then I'd write the probabilities. Instead of these, I'd write it 0.45. Okay, I take a half times 0.9 is 0.45, and then the chance that you go down for x, which is 0.5, and up for y, which is minus 0.4, which is also 0.45 here. Okay, then I'd go 0.05 here and 0.05 there. So here, knowing that y has a good outcome tells you nothing about what x is going to do. It's still equally likely x was good or bad. Knowing that y had a bad outcome, x is still likely to be equally likely good or bad. Okay, and similarly, knowing the outcome of x tells you nothing about the outcome of y. This is 9 times this, and this is 9 times that. So the yellow is independence, okay, which is probability x equals x times and y equals y equals the product, probability x equals x times probability y equals y. So that's the case of independence. So in the case of independence, knowing something about one variable tells you nothing about what happened to the other variable. But you could do other joint things. So knowing each of them separately doesn't tell you how they're jointly distributed. And the covariance is an effort to see whether they're sort of correlated together or whether they're correlated independently. So independence, by the way, independence implies covariance equals 0. Okay, and that's obvious because what's happening in the x variable has got nothing to do with what's happening in the y variable. So since it's linear in x, you can hold y fixed, and the x is just the same, and you're going to get something that adds up to 0. So for any fixed value of y, this number will just give you the expectation of x, which won't depend on y, and it's going to be 0 in every case. So therefore, if they're independent, the covariance has to be 0. Okay, so independence means x and y tell you nothing. That means the covariance is 0. They could be positively distributed like up here or negatively distributed, either way you want to do it. Does that make sense? You asked me about this.
Yeah.
Okay. All right, so what are the key simple observations here that are going to inform a lot of our behavior under uncertainty? Well, it's going to turn out that expectation is good and standard deviation is bad. Okay, so if we take this variable that we just found, x and y were both here. X and y were both there. Right? They each had standard deviation 1 and expectation 0. So this is the standard deviation. So x is here, and by the way, so is y. Same thing. Well, suppose I put half my money into x and I put half my money into y, and if I put half my money in each, let's say I get half the payoff of each. Okay, I make half a bet and I get half the outcome. What happens to my expectation? Well, the expectation of that obviously equals a half x bar plus a half y bar, which also equals 0. So it's staying the same. The expectation hasn't moved. But what's the variance of a half x plus a half y? Okay, well, by that formula, it's the covariance, so I'm just going to do this formula. I'm going to do a half here and a half here. Okay, so it's the same thing. So it's the covariance of a half x with a half x plus the covariance of a half x plus a half y plus a half and a half. Okay, but the covariance of a half x with a half x is just, okay, what is that? It's the variance of a half x. But we already saw from our definition of variance over here, remember, if you double x, you're going to multiply the variance by 4 because you're squaring things. Okay, so this is going to turn out to be a quarter times the variance of x. And this, which is a half y and a half y, is going to be a quarter times the variance of y. And if the two are independent, the covariance will be 0. So in this example of these two variables, if I take the orange distribution where they're independent, you know, I can do an x outcome and have this standard deviation and this expectation, 0 expectation, and that standard deviation. I can do the y thing, get the same standard deviation, or I can put half my money in each. It seems like a total waste of time to put half my money in each. After all, they give me the same standard deviation. But no, it isn't. If they're independent, you're shockingly, drastically reducing your standard deviation. Because if they're independent, the covariance is 0. And so this plus this, the variance of x equal the variance of y, is just the half the variance of x equals half the variance of y. Okay, so that's shocking. So the standard deviation, therefore, the square root of that is 1 over the square root. So by putting half your money in each, you've now produced this when they're independent. So this is the standard deviation of 1/2 x plus 1/2 y, x, y independent. You move from this point to that point. So you reduced your standard deviation without affecting your expectation. Okay, so the first lesson that we're going to see applied, this is all mathematics, so, mathematicians understood this, of course, a long time ago. But to realize this has an application to economics wasn't so obvious. So this is the thing, although Shakespeare knew it, it's diversification. So don't put all your, spread your investments out into different waters. Shakespeare, Antonio had a different ship on each ocean. So instead of putting all the ships on the same ocean, he put them on different oceans, which he assumed was independent. So he had the same expected outcome, assuming the paths were just as quick to wherever he was selling the stuff. Same expected outcome, and that each of the waters were equally dangerous, but he drastically reduced his variance. And because there were a lot of oceans and a lot of ships, this number went down further and further. So the key is to look for independent risks. Okay, so that's one lesson in mathematics that has a big application in economics. What's a second thing? Well, the second thing is that if you add a bunch of risks together, so I'm going to say this loosely, so this is, if you add a bunch of risks together, so by the way, what's a generalization of this? Before I say this, if you had n independent risks with identical means and variances, okay, means, let's call them all x bar, and variances sigma squared. Okay, let's say they all have expectation E and standard deviation sigma squared, variance sigma squared, each of them has that. Then what happens to the Okay, so each of them has standard deviations. So they're all identical, like x and y have the same expectation 0 and the same standard deviation 1. Suppose I had 20 of those and I put 1/20th of my money into each of them. What would happen to my expectation? 1 over n dollars in each one implies what happens to my expectation. If expectation equal to what? Each of them had expectation E. I now split my money among all of them, all with the same expectation. That also has to have expectation E. All right, just like this thing, putting half my money in Y and half my money in X, wherever the X went, Y was over here, X is there. Half my money in X and half my money in Y is going to give me the same expectation. If I had 12 projects like that that were independent, I'd still have the same expectation. But my standard deviation, what's going to happen to my standard deviation? Well, the variance is going to be, so what's going to happen to the standard deviation? By what factor? So the variance, so each, it's going to be, yeah, what's going to happen to the variance?
1 over.
Put 1 over n dollars in each of n identical but independent investments. What will my variance be? The variance is going to equal 1 over n times sigma squared. Why is that? Because each one will have 1 over n dollars in it, so its variance is going to be 1 over n squared times sigma squared, but there are n of them. Okay, so it's going to be n times 1 over n squared, so it's just 1 over n. So it implies the standard deviation, which implies the standard deviation, so I'll call it standard deviation, is 1 over the square root of n times sigma. Okay, so it's just as generalization. We've got 1 over the square root of 2, so if I did n of them instead of 2 of them, I'd have 1 over the square root of n. So those turn out to be very useful formulas, which are going to come up over and over again. And let's just say it again so you get this straight. If I have 2 independent random variables and I split my money evenly between them, and they have the same expectation, doesn't have to be 0, it could be a positive number. If I split my money between them, I haven't changed my expectation, because each dollar, however I split it, I'm putting into something with the same expectation. But because they're independent, you get a lot of off-diagonal things happening. The off-diagonal things, remember, are canceling. One investment's turning out well, X's, sorry, that's on the diagonal. The off-diagonal elements are good in a way, because if one investment's turning out well, turning out badly, the other one's turning out well. So here, investment Y is turning out badly, but X is turning out well. So to the extent you're off the diagonal, you're canceling some of your bad outcomes, because one's good and the other's bad. So that way, you leave the expectation the same, but you reduce the variance. In fact, it would be even better if you could put everything on the off-diagonal. But to the extent you get at least some stuff on the off-diagonal, you're reducing the risk. Okay, and how fast you reduce it when they're independent? You reduce it dividing it equally, because the variance is a squared thing. Half your money in one and half in the other means the variance of the first is a quarter, and the variance of the second is a quarter. But now there are 2 of them, so the total variance is a half of what it was before. If you have 10 of them, each one is a tenth the money, so it's got 1/100th of the variance, but there are 10 of them, so it's 10/100ths, 1 over n of the variance. If you take the standard deviation, it's 1 over the square root of n. Okay, so that's the rate at which you can reduce your uncertainty and your risk. And we're going to come to, you'll see this gets much more concrete in next lecture. But one more, okay, so this is just stuff that most of you know. So one more thing. If you add a bunch of independent things together, independent random variables, so I'm going to speak very loosely now. Variables. You get a normally distributed random variable. Random variable. Normally distributed random variable with the corresponding expectation, and standard deviation. Okay, now, so if you take these, you take half your money in each. So if you took, okay, so what am I saying? Okay, so I don't want to speak too precisely about this because if you've seen this before and seen a proof, you know everything about it. If you haven't, it's just too many subtleties to absorb. But the normal distributed random variable is the bell curve that looks like that. Wasn't too, okay, looks like this. Okay, so there's the bell curve with expectation 0. Okay, so it's this bell curve. Now, what's special about it? It has a particular formula, which has got an exponential to a minus x squared thing, and it's got a particular formula to it, which if you know, you know. If you don't, it's written down. We're never going to use the exact formula. But it looks like that. So these are the outcomes x, and this is the probability of outcome, or frequency of outcome. Okay, so the bigger x is, and this is the mean, equals 0. I've assumed the mean is 0. So this is, if you take a really big x, it's very unlikely to happen, and a really small x is very unlikely to happen, and x is near the mean or pretty likely to happen. So anyway, it's amazing that if you add this random variable to itself a bunch of times, it can only produce 1 and minus 1. Right? This one produces totally different outcomes. A third and minus 3. They're completely separate they're disjoint outcomes. But if you add this together, you know, you can get 25 1s and 10 minus 1s, so that gives you 15. Over here, you know, you could have 25 will never get me there. So you could have, so sorry, that was a bad example. If I had 30 things, I could get, you know, 18 1s and 12 minus 1s. That'll give me 6. You could have gotten 6 over here, but with 30 outcomes, you could get, you know, all 30 of them could have turned out to be 1, and that would have gotten you pretty close to the same outcome. So it's not, you know, just because these outcomes are separate. Once you're adding them up, you're starting to produce numbers different from 1 and minus 1, you know, and these added up, if you take the right combination of 1/3 and minus third, you can start reproducing things. Like to get a 1 here, you could reduce 3 tops, and then you're producing a 1. So anyway, the shocking thing is if you add a bunch of these random variables that are independent to each other, you get something normally distributed that looks like that, because this random variable had exactly the same mean and standard deviation. You add the same number of these, you're going to get outcomes that are almost identically distributed. So in the limit, this random variable, enough of these added together, looks exactly the same as these added together. Okay, that's the second surprising mathematical fact. And the third thing that we're going to use is that the normal distribution is characterized by the mean and standard deviation. That's all it takes to write the formula of this down. And these numbers, these are called thin-tailed. These probabilities go to 0 very fast. So you shouldn't expect many outlying dramatic things to happen. Okay? And in the world, they do happen. And so we're going to see that much of classical economics is built on normally distributed things. And so you can't see, you shouldn't expect any gigantic outliers to ever happen. And it seems natural to build it on that kind of assumption, because if you add things that are independent, you get normal distributions all the time. And things seem independent. So why shouldn't you get normal distributions? And yet, we must not get it because we have so many outliers. Okay, so that's the basic background of mathematics. Are there any questions about any of that? I'm just assuming you know all that, and now we're going to move to economics. Okay, I think that's all the background you need. Okay, so I want to do one more thing, which is maybe background, but it's quite a, it's used in economics all the time. Okay, and it's called the iterated expectations. Okay, so if I told you that these variables were correlated, like these up here, like the orange things, if I told you what x turned out to be, that would tell you a lot about what y was going to be. So for example, if I told you that x was, sorry, the white ones, or the correlated ones, if I tell you that x has turned out to be 1, that tells you that y has to be a good outcome of a third. Because if x is 1, this never happens. So the only thing that can happen if x is 1 is that y turns out to be a third. So knowing x is going to completely change your mind about the expectation of y. So conditional expectation, I should have said this before, conditional expectation simply means recomputing expectation using updated probabilities from your information. Now, you've probably done this in high school, so I'm just going to assume you know how to do this. So in this case, if I tell you something like x has turned out to be 1, that tells you that only these two outcomes are possible. So that means that the only two outcomes in the white case have happened with probability 0.5 and 0. But if I tell you x has come out to 1, the conditional probabilities have to add up to 1. So you just scale things up. So you know that y had to have been the good outcome up here. Okay? If I tell you that the bad outcome for y has happened, okay, then you have probabilities of x of 0.1. Okay, so the 0 makes things too easy. Suppose I tell you that the good outcome of y has happened. What are the chances now that x has gotten the good outcome in the white probability case? If I tell you that y turned out to be a third in the white probability case, what's the probability that x turned out to be 1? Conditional on that. 5/9. Okay, so that's it. Because the probabilities are now, you're reduced with 0.4 and 0.5, so 5/9 of the time. Okay, so that's an idea which I assume you all can, it's very intuitive and it's way too long to explain, and I'm sure you know how to do that. So anyway, the conditional expectation, blah. So the iterated expectation is simply this. It's an obvious idea, but it's going to be incredibly useful to us. It says, if you ask me, what are the chances that the Yankees are going to win the World Series against the Dodgers, let's suppose that's who it's going to play, the Yankees are going to beat the Dodgers, what do you think the chance, what's the probability that's going to happen? What do you expect the chances are? If I then ask you my opinion after the first game, well, obviously if the Yankees win the first game, my opinion's going to go up. So I'm going to have a different opinion. If the Dodgers win the first game, my opinion is going to go down. So I'll have a different opinion. But you can ask now another question. What's your expected opinion going to be? So the law of iterated expectations is the expectation of x has to equal the expected expectation of x given some information. So here's what I think. The Yankees are 70% likely to win. If I say after the first game, I'll think it's 80%. And after the first game, if the Dodgers win, I'll think it's gone down to, 65%. It had better be that the average of my opinions after the information is the same as the number I started with. Okay, that's just common sense, and I'm not going to bother to prove that. So that's incredibly important that it's not only the expectation of x, but as you learn stuff, you can anticipate your opinion's going to change, but your average opinion has to always stay the same as x was. Okay, so that's the last of the background. And now I want to do a simple application of this. So in fact, to that very question, suppose that you're playing a World Series. The Yankees are playing the Dodgers, and let's suppose that the Yankees have a 60% chance of winning any game. I'll just do it here. Yankees have a 60% chance of winning any game. What's the chance the Yankees win a 3-game World Series? How do you figure that out? Well, a naive way, a simple way of figuring that out is to say, well, what could happen? Life can mean a Yankee win, let's call that an up, or a Yankee loss, let's call that a down. Okay, and this could happen with probably 0.6 or 0.4. The Yankees could win again. Okay, so that's probably 0.6. We have 2 Yankee wins. Or the Yankees could lose the second game, so that's probably 0.4. The Yankees could lose or could win. That's 0.6, and this is 0.4. Okay, and we've only played 2 games. The Yankees could win a third. Well, you don't need to play this game because they've already won a 3-game series, but if you did, it wouldn't matter. 0.4. Or we could go up or down. Okay, the Yankees, after winning and losing, could then win, probably 0.6, or could lose. Okay, or after losing and winning, they could win again, or they could lose. After losing and winning, they could lose. So this is probability 0.4, and this is 0.6. And then finally, we have this, and we have this. So this is 0.6 and 0.4. Okay, so this is what the tree looks like. You could imagine 8 possible paths, each of length 3, where you give the whole sequence of wins and losses. So to compute the probability that the Yankees win, you look at all the, so in this case, the Yankees win, right? They would have already won here, but if you play it out, it doesn't matter. They're going to win here and here. They've got 2 wins and 1 loss. Here they've got 1 win, 2 wins and 1 loss. They win. Here they've got, loss, win, win. They win the World Series. Here they lose, win, lose. They lose the World Series. Here's lose, win. It's win, lose, lose. They also lose the World Series. Here it's lose, lose. They've lost the World Series. Loss. Okay, so these are the possible outcomes. So you could compute the probability of every path. There are 8 of them. And then multiply that probability by the outcome, and you'll get the chance that the Yankees will win the World Series. Right? That's clear to everybody? But there's a much faster way of doing it and putting it on a computer. Okay? And that's using the law of the iterated expectation. So first of all, so this is called a tree. So we're going to use trees all the time. So tree, I don't want to formally define it. It's just you start with something, and stuff can happen. Stuff happens every period, and so you just write down all the things that can happen. And then you write down all the things that can happen after that, and the thing unfolds like a tree. That's formal enough to describe a tree, and here we've got it. But you notice that the tree, the number of things happening, grows exponentially. It's horrible to have to compute something growing exponentially. But they're often recombining trees. Oh, so if I ask, by the way, in this tree, whatever the opinion is here, which turns out to be 0.68 something, yeah, I should have asked you to guess, 0.68 something. If you write down the opinion, that opinion has to be the average of the opinion here and the opinion here. So if I take the opinion here times 0.6 plus the opinion here times 0.4, that's also going to equal 0.68. Okay, and that's what's going to be the key to computing the thing much faster, rather than going through every branch, which is such a pain. Okay, so because they're an exponential number of exponentially growing number of paths. Very bad to have to compute by hand. But we noticed that we could look at a recombining tree. Okay, these 2 nodes are essentially the same. What difference does it make if the Yankees win 1 and lose 1, or lose 1 and win 1? In both cases, they're at the same spot. They're even in the World Series. And since we assume the probability of winning any game is the same, 0.6 and 0.4, independent of what's happened before, you might think you're learning, something about, their starter pitched here, and, he didn't last the whole game and stuff like that. So I'm not allowing for any of that. I'm just saying it's a 0.6, 0.4 chance for the Yankees to win no matter what happens. So all you care about at any point from then on is who's won how many games. So these nodes are basically identical. And these nodes are identical because it all ended up with the Dodgers ahead 2-1. And here the Yankees were ahead 2-1. And here the Yankees were ahead 3-0 and 0-3. So the recombining tree, which has all the same information, is just this, 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 okay, this tree. So this tree only has 1, 2, 3, 4, 5, has it's 1 node, 2 nodes, 3 nodes, and 4 nodes as time goes by, growing linearly instead of growing 1 to 2 to 4 to 8, which is growing exponentially. So I could have a very long World Series and write it as a finite tree and just put 0.6 and 0.4 here at every stage. Okay, so how am I going to solve this now? Well, over here, I know the Yankees ended up winning all 3 games. Here they won 2. Here they won 1. Here they won none. So those are the outcomes. So instead of trying to figure out path by path with these exponential number of paths what the chances of each path are, well, it's hard to compute. Here it's 0.6 times 0.6 times 0.4, complicated calculation. Okay, I'm now going to do something simple. I'm going to say, what would I think if the Yankees had already won 2 games? Well, I know that they would win. Okay, that's a 1. The series is already over. What would I think after the Dodgers won the first 2 games? I know it was over. What would I think? And so how did I get that? It's 0.6 times 1 plus 0.4 times 1. That's 1. The Dodgers, 0.6 times 0 plus 0.4 times 0. That's 0. Okay, so that's my opinion if the Dodgers win 2 games. Here's my opinion if the Yankees won 2 games. What's my opinion? What would my opinion be if they split? Well, if they split, what would my opinion be? If I started here, so after game 2, they've each won 1 game. I don't know who won the first one, but it was 1-1 after 2 games. Now what would I think? Exactly. So it's 0.6. It's 0.6 times 1 plus 0.4 times 0. So the odds, I would think, the Yankees would win the World Series here with 1 game left, knowing that they win 60% of the time, it's 0.6. But now, what do I think if the Yankees win the first game? What's my opinion? So it's 0.6 times 1, so it's 0.6 plus 0.4 times 0.6. So that's 0.24. So that's 0.84 here. And what's my opinion after the Yankees lose the first game and the Dodgers win? What do I think is going to happen? What will my opinion be here? It's 0.6 times having an opinion of 0.6, so it's 0.36, plus 0.4 times knowing that's all over, plus 0.4 times 0. So it's equal to 0.36. Okay, so so I've now figured out, not only am I solving this thing much faster than I could over there, but I'm finding interesting numbers on the way. I'm now figuring out, what would I think after the Yankees won the first game? Well, now I think it's 84%. What would I think after the Dodgers won the first game? I think it was only 36% chance of the Yankees winning. Okay, and so now what's my opinion at the very beginning? It's 0.6 times 0.84. It's my chance of having this opinion plus my chance of having that opinion, plus 0.4 times 0.36. Oh, no. 504 maybe plus 2144. What is that? 0.648. 6 times 84 looks like 504, and 4 times 36 looks like 144. So it looks like 0.648. Okay, maybe that's what you said. So that's it. I've solved it now. Okay, so that's the method of iterated expectation, and we're going to turn this into quite an interesting theory in a second, but I want to now put that on a computer to show you just how completely obvious this is. I mean, not obvious, fast this is. So you could solve for any number of a series of any length you could instantly solve. Okay, and now we're gonna price bonds that way too. So class. Okay, so what did I do? This is a spreadsheet you had. I simply had the probabilities of the Yankees winning, which was 0.6, which I could change. Oh. Okay, so this is the simplest thing to do, but now suppose that, okay, so we said the Yankees can win every game with probability 0.6. So then what did I do? I went down to here. I gave myself some room. I didn't do a very long series. So now what does each of these things say? Each of these nodes, like that one, says, if I can read it, it says, so this is my opinion of winning the World Series. It says, my opinion here is going to be the chance I go up Okay, that's the probability, that's A2, that's 0.6, the chance I go up, times what my opinion would be over here, plus the chance that I go down, which is here, chance I go to here, which is 1 minus that number 0.6 that's frozen up there, times whatever I thought would be my opinion here. So you see that's the same. I just write that once. I wrote that once here, that thing about, the probability. My opinion there is the probability of going up. That's SA, $2, that's 0.6, it's frozen, times what my opinion would be on the square over 1 and up 1, plus 1 minus $2, times my opinion over 1 and down 1. So I just copied that as many times as I wanted to down the column, and then I copied it again across all the rows. So all of these entries are identical. They're all just copies of each other. Okay, so it just says iterate your opinion from what you know it was forward. Okay, now how do I take a 3-game World Series? Well, we're starting here. This will be game 1, game 2, game 3. So all I have to do now is put ones everywhere. Here, like 1, enter, and now I'll copy this, control copy, and go all the way down here, because when you're above the, okay, so that's it. So we've got all the numbers. Okay, so why is that? Because my opinion here, remember the numbers we got? The series goes 1 game, 2 games, 3 games. So if you end up above the middle, that means the Yankees won the majority of games. Your payoff is 1. Okay, your probability of the Yankees winning is 1. Okay, and so now what's your opinion going to be? If you've won 2 games, then the Yankees have to have won. Okay, what if the Yankees win the first game? Well, you remember the numbers we got? 1 and 0.6 and 0. So here's the 0.84 is the average of 1 and 0.6. Here's the 0.36, which was the average of 0.6 and 0. And then we come down to the middle, which is 0.648. Okay, so it's what do I do if I want to play a 7-game World Series? Okay, I have to get rid of this. And if it's a 7-game World Series, I would now I want to restore what I had before, so I'm going to copy all this, control, copy, control. Okay, so I'm back to where I was before. So this was, okay, so you see what I'm doing here? This is, game hasn't started. This is the first game, second game, third game, fourth game, fifth game, sixth game, seventh game. Every square is just saying my opinion is my average of what my opinion will be next time. If I want to make it a 7-game World Series, I just plug in ones here. There must be some faster way of doing this, but I plug in ones here. So control copy, and here are all the ones down to above the thing, control V. And now I've solved my opinion backwards. And I've got the chances of the Yankees winning a 7-game World Series are 71%. So the longer the World Series goes, the better the chances are the Yankees win if they're better in each individual game. And you can do it instantly. So are there any questions about that? Okay, so that is a trick we're going to use over and over again to price bonds. You do it by backward induction because of the law of iterated expectations. Your opinion today of what's going to happen way in the future when you get a lot of information has to be the average opinion you're going to have after you get some information, but before you know what the final outcome is. And so realizing that, you just take the pieces of information one by one and work backwards from the end. And you can solve things instantly, which would take, in the brute force way, an exponentially growing length of time to do if you did them path by path. Okay, so let's now, I now want to turn to an application of this to one subject, which is, let's just not do the World Series. Let's do a more interesting problem. I hope I have time to finish this story. Okay, so the more interesting problem is this. Let's suppose that let's suppose our uncertainty is of a different kind. Instead of not knowing the outcome of the World Series, let's say we don't know how impatient we are. So remember, the most important idea so far that we've seen, because we haven't done uncertainty yet, the most important idea we've seen so far is impatience. That's the reason why you get an interest rate, and the interest rate is the key to finding out the value of everything. So Irving Fisher put tremendous weight on impatience. And now that we're talking about uncertainty, the natural thing to make uncertain is how impatient you're going to be. So we want to talk a little bit more about impatience. So, impatience by Irving Fisher is the discount. So, in fact, I want to talk about this in sort of realistic terms. Do we really believe that people just discount the future? You know, that 1 year they discount by delta, 2 years they discount by delta squared, 3 years by delta cubed, 4 years by delta to the fourth? Is it really true that every year people think of as delta less important as the year before? I mean, the arguments for that is, you know, you might not live beyond a certain, you know, poor imagination. So imagination, poor imagination, we've said this before, poor imagination and mortality are the two arguments for discounting. But let me tell a story that seems to contradict that. Suppose someone asks you to clean your room, and they give you a choice of doing it. I'm thinking of my son, for example. Say, hey, clean your room, Constantine. And so if I say, do it today or do it tomorrow, that makes a huge difference to him. I mean, just a huge difference. Doing it today for doing it tomorrow. He'll think doing it today is just impossible. Doing it tomorrow, you know, I can almost force him into agreeing to that. So clearly there's a big discount between today and tomorrow. But what about between today, what about between a year from now and a year and a day from now? Do you think Constantine will think there's any difference from that in that? And the answer is no. He just, you know, if I say, Constantine, do you agree to clean it a year, 365 days from now, or 366 days from now? To him, there's hardly any difference. But, you know, there's hardly any trade-off. One is hardly more valuable than the other. Of course, they're both pretty unimportant, but the ratio of the two doesn't even seem important to him. So that's called hyperbolic discounting. If you do any experiment with people or with people or with animals, you know, you make a bird do something, and, you know, if he does more stuff, he gets the things faster. You know, he'll do a lot of stuff to get it in the next minute as opposed to in 2 minutes. But the amount that he won't, the difference between what he'll do in 10 minutes versus 11 minutes is very small. Okay, so hyperbolic discounting is discounting much. Hyperbolic discounting is discounting much less than exponential discounting. So this has a tremendous importance for the environment. If you thought that people exponentially discounted, like they thought each year was only 95%, if the interest rate's 5%, it sounds like the discounting is 0.95. So if next year's only 95% as important as this year, and the year after that is only 95% as important as the first year, and the third year is only 95% as important as the second year, 0.95 in 100 years to the 100th is an incredibly small number. So there's no point in doing something today and investing a lot of resources in order to clean up the environment and help people 100 years from now. Because by discounting it this much, nobody could, you know, what's the difference? Because the future is so unimportant. You shouldn't be investing resources now to do something that's going to have such a small effect later. So in all the reports on the environment, a crucial half of the report is devoted to what the discount rate should be. So, but they never thought of doing the most obvious thing, which is to ask, what would happen if the discounting was uncertain? All of these are certain discount rates. So what if you made the discounting uncertain? What would you imagine doing? So suppose you discount today at 100%, and maybe next period you're going to discount at 200%. This is the interest rate. And here it might go down to 50%. It could go up to 400%. Or it could go down to 100% again. Okay, or it could go down to 25%. You know, this kind of discounting I have in mind. You don't know, so delta equals 1 over 1 plus r, and this is r. R0, r up, r down. Okay, so maybe the discount is uncertain, and it goes like that. So it's a geometric random walk. I keep multiplying or dividing by 2. I multiply or divide by 2. I multiply or divide by 2. That seems to make for a lot of discounting. These numbers are going up very fast. It seems like, the higher the R, the less you care about the future. So the question is, if you ask for $1 sometime in the future, what will people be willing to pay for it? Okay, so you know today that you think the future is only half as important as the present. Let's say these all have probability of half. Okay, and tomorrow, it might be that you think the future is only 2/3. The next year is only 2/3 as important as that current year. Or you might think the future is only 1/3 as important as this year. So you see how this is working? 2 years from now, you might think the future is only 1/5. The third year is only 1/5 as important as the second year. Here you might think the third year is half as important as the second year. Here you might think it's 4/5 as important as the third year. Okay, so you don't know what it's going to be, and if anything, this process seems to give you a bias towards getting really high numbers. Okay, high discounts, meaning the future doesn't matter. Okay, so, but nobody bothered to stop. So this is the most famous interest rate process in finance. This is called the Holy interest rate model, where you think today's interest rate might be 4%. Maybe it'll get maybe it'll be 10% higher next year or 10% lower. And it'll keep going up and down like that. And that's the uncertainty about the interest rate. So if we think interest rates are so important and patience is so important, and we want to add uncertainty, first place to do it is to the interest rate. And the Holy model in finance does that. Nobody bothered to compute this out more than 30 years. Okay, suppose you compute what out? Suppose you get $1 for sure in year 1. Okay, how much would you pay for $1 in year 1? Well, your discount is 100%. You'd pay $0.50. How much would you pay for $1 in year 2? $1 in year 2, well, you know how much more $1 now is worth than a year from now, but you don't know 2 years from now, so you have to work by backward induction. Here, $1 for sure is worth $1. What would I pay for it here? I'd pay 1/3 of $1. Okay, and what would I pay for it here? Well, the discount is 2/3. I'd pay 2/3 of $1. So what would I pay for it back here? I'd pay half times 1/3 plus half times 2/3 discounted by 100%. So that's some low. So it's a half. So it's 1/3 plus 1/6, which is a half times a half, which is a quarter, I guess. Okay, so I'd pay 1/4. So for any time, I could figure out d of t equals amount I would pay. I'm going to be done in 1 minute. Amount I would pay today for $1 for sure at time t. And that number, obviously, is going to go down as t goes up. So, and we know how to compute it by backward induction. You just put the ones further and further out, and then you go backwards by backward induction. But just like for the World Series, I could do that for any t, however big I want to. And on a computer, in the spreadsheet, which I wrote for you, you could do this instantly. Okay, and nobody bothered to do this for t bigger than 30, because bonds basically don't last for more than 30 years. So what's the point in doing it for t bigger than 30? So 100 years, there are virtually no financial instruments that are 100 years long, so they didn't bother to do this. Suppose you did it for every t, up to 1,000 years. Well, you could do it on a computer very easily. You could even prove a theorem of what it's like. So in the problem set, I'm going to ask you to do a few of these, and what you're going to find is that people are hyperbolic, that you get you discount a lot. Like, it's pretty close to 100% for the first few periods, but after that, you're going to be, anyway, you're going to find out what the numbers turn out to be when you do it in a computer. Okay, so we're going to start with random interest rates next period, the most important variable in the economy.